Alright, so this is going to be a little bit of a shorter one. We're talking about thin wall pressure vessels. So basically something that you have that's pressurized. So like there's some kinds of pressurized containers you might find. Like here, let me pull one up. So like you can see right here is an example of like a cylindrical one you might have, or you might have like a spherical one. And in general, you don't want these things to like explode or like puncture or something. Like you see this, I don't know what happened there. But you know, being able to design these things so that they don't break under the like stress or the pressure that they get from whatever they're containing, usually a pretty important thing. And so the two kinds that we're going to look at are the spherical and the cylindrical ones. So I guess we can go ahead and start with the cylindrical. Our model for this, basically what we're going to do is we're going to say that we have some load or some pressure from whatever's inside here, like the gas or whatever, which is going to equal, my force. So this is going to be pressure times area. So basically we have P times, and then technically for the area, we would have to figure out like how perpendicular it is. But we're going to make the same assumption we did with the bearing and just assume that it's basically distributed across this entire kind of cross-sectional area evenly. The error is like less than, I want to say 5%. So yeah, this is going to be P pi r squared. And then this area right here, basically what's holding it out is all of this green area. So basically the thing that's holding it together in the spherical case is all of this green area, right? So what we can say is that our pressure, which is lowercase p or uppercase P, times pi r squared, usually uppercase P is like our loading, right? But anyway, P pi r squared has to balance with, and then we're going to say sigma, which is whatever is right here. So this is sigma attached to this green part, times 2 pi r t. So this right here is our circumference times t, which is the thickness. This isn't actually the area across here, but again, it's an approximation. It makes our math a lot simpler. And I think what they say specifically is that if r is greater than or equal to 10 times the thickness, then the error is less than 5%, which is usually good enough, especially if you have like a factor of safety or something, right? So we can go ahead and we can solve for sigma. We get that sigma is equal to P times R over 2T. Our pi's cancel, one of the R's goes away. And because we're looking at basically a little segment on the outside here, the pressure is going to be the same in all directions, right? Because you can imagine I could do this around this axis right here, or I could do it around this axis right here, or really any axis where I'm splitting it in half. So we're going to have this pressure. This would be related to this side right here and right here, but I'd also have an equal pressure if I did an analysis where I split it like across this line. I'd have an equal pressure right here, and all of that is normal, and I would have no shear. So if you remember, a state where we have all normal and no shear stress is the maximum or the principal, right? So if I go ahead and I graph this, if we have like this right here is my shear, and this is my normal stress. So this is my sigma axis, tau axis, right? Basically, I would have my tangential, which is this PR over 2T, and then I would also have a 0. That 0 would be basically the in and out of plane. And then my shear would look like this, right? And this would also go down because it's a circle, so it would go down like this. So basically my max shear would be PR over 4T because it would be half of this diameter, which is my sigma right here, PR over 2T. So yeah, that's about it for the spherical. The only other thing I would say is that there is a difference between whether you're on the outside or the inside of the sphere. So if you're on the outside, we're saying that there's no radial pressure because the pressure that we're putting in here is what's called the gauge pressure, which means it's relative to the outside pressure. So basically, what we're saying is that we're going to let the outside pressure be 0, and then this P right here is equal to the difference in pressure from the inside to the outside. So, right? So if I'm looking at an element on the outside going into here, I would have 0 pressure. But if I looked at an element that's on the inside of this wall, I would have a normal pressure pointing into it like that of P in addition to my PR over 2T in basically these transverse directions, so right here and right here like that. Now in the cylindrical case, it's not going to be symmetric, and we're actually going to have a different stress depending on which direction we look at. So if you look at basically this kind of longitudinal direction, it's going to be exactly the same. We're going to have our pressure right here, P pi r squared. This is equal to my load. This right here is a capital P. I'll just go ahead and like underline it so you know it's a capital, right? And then this would have to be balanced with my stress times my area. So right, sigma times 2 pi RT. We would do all the calculations. So sigma longitudinal equals PR over 2T, same as before. But we also have this stress, which is called the hoop stress, which is basically wanting to break it apart in this direction right here. So for this, we're going to have, again, our pressure coming in like this. We're going to assume that it's normal distributed across this square, which is an approximation, but the air is low enough that we can use it in a like an actual design if you're going to use a factor of safety or something. So we're going to call this is our load. I think they use axes here, so they say like this is the z-axis or whatever. So we have like our x, y, z axes. If you want to do that, let me make these a bit more aligned. So this is like this way, right? This way, z, x here, y here. This is equal to my pressure times 2 r delta x. All of those are multiplied. So basically, what we're saying is that my delta x is like whatever this right here happens to be, right? So my width right here, r would be the radius, so this whole length right here would be my diameter, or twice the radius, and then my thickness is the thickness of this little bit right here. So this right here is my t. I would also have a t down here, just like that. So if you think about this, I have delta x times 2r, that's my area, times my pressure will give me my load, and then that has to be supported by this area right here plus this area right here. So basically the area we're going to have is delta x times t times 2. So if we go ahead and we write this out, so this is my right here, sigma 2t delta x, and these have to equal each other. So like I said, my normal stress times 2t delta x has to equal the internal pressure times 2r delta x. Delta x's cancel, which means it doesn't matter how wide of a segment we're looking at, because we really just care about the stress that's breaking it in this direction right here. And then I can just divide over the 2t, right? So I'm going to get that sigma is equal to p r over t in the hoop direction, and that's it. So you can see that my hoop stress is going to be twice as big as my longitudinal stress, which means that as I increase the pressure, the first direction that this cylindrical vessel is going to fail in is going to be in the hoop direction. Now you could also technically have like a negative pressure, and basically what would happen there is it would collapse inward. I've actually seen a video of it. It's pretty neat. So again, if we want to go ahead and graph this, we would now have our vertical axis right here, horizontal axis. This horizontal axis we're going to call our normal stress, and then this right here is our shear stress. We're going to have the absolute max, which is our hoop, PR over T, and then we'll also have a case of our PR over 2T. This is one of our stresses, and then lastly we have the radial stress, which is 0. So basically, between our three planes, the x, y, and z, if we're rotating our element basically and looking at the different directions, what shear and what normal stresses we're getting, we're going to have circles that go like this for two of our planes, and then our absolute maximum shear is going to be a big circle. Sorry, these are really hard to draw, but like a big circle basically connecting to here and to here. And then, yeah, I know this is really bad, but our maximum absolute shear on our element is going to have to be half of this diameter, or the case of the radius, which is PR over 2T. So yeah, that's it for our pressure vessels. We can go ahead and add the stress that we get from pressure vessels. If we're looking at something that's pressurized, that's also under loading, we'll go ahead and take a look at an example of that later.